my talk will be more focused. My talk will be more focused on the kinetic modeling because many of the what is it research papers they focus on the use of the different feedstocks, develop different catalysis, and somehow they have used different mechanisms to intensify the process also. But there are very few limited studies which discuss about the mechanistic behavior, that is the exact know how the intensification approach can be utilized and how to quantify them on the basis of which parameters. Okay, so the talk title is, as already suggested or discussed, it is synthesis of biodiesel from a blend of mixed non-edible oil using the heterogeneous catalyst and role of sonication in process intensification. So if you have any query, anyone, so they can ask me in between also or at the end also. So there is no problem. Okay. So yeah. So before starting to the biodiesel, so why we are considering the biodiesel and all those things. So let's discuss in brief. Okay. So we all know that the fossil fuel resources are limited and the consumption is increasing day by day. And with this increasing consumption, the prices also increasing of the fuels, as well as the CO2 emissions is also increasing, and there are environmental regulations, and we have to minimize the CO2 emissions in upcoming years. So the alternate route is that we can generate the fuel from the biomass, which is renewable, and whatever CO2 is we are eliminating in the atmosphere, so that can be recycled. So this is the whole concept. So that's why for last 2 decades, the focus is shifting on the biodiesel, either in the 100% form, or it may be the what to say, either in the blends of 5%, 10%, 15%, 20%. So this is like this. Okay. So this first graph is gives you idea about how the oil consumption is increasing. Okay. So of course, this data is little older. Okay, but you can see that the average growth, if we can consider, so average growth is increasing around 1.5 to 2%. Yeah, maybe last year due to COVID, the consumption was decreased, but the change reported by the IEA in the year, in this current year, in the month of March, it is saying that we have already reached the pre-COVID situation of the oil consumption in case of, typically in case of the India. Okay. So again, number of vehicles increasing, so we have to think about it. Nowadays, people are discussing about or taking into consideration of the electric vehicles. Okay, so definitely, as per the report of IE again, the fuel consumption of the crude oil, of the part of crude oil that is used for the fuel consumption, is expected to decline in upcoming years, but that decline is not that much greater. It is just below than 0.5%. Okay, but at the same time, the consumption of crude oil for the petrochemical and other sectors remain increasing, and they have reported, especially in terms of the Asian countries and typically in the Indian countries. So they found that the consumption of crude oil in case of the petrochemical as well as fuel sector is again remain in the demand, and there is no decline in the this demand. Okay, so based on these consumptions or this scenarios, we have to look for the alternate fuels. And when we say alternate fuels, so it should be what to say, cost economic, it should be renewable, it should be, if it is green, then it is well and good. If it is not green, then it should be what to say, minimum damaging to the environment. Okay, so biodiesel, then biobutanol, bioethanol, biogas, these are some alternate fuels that came into picture. And in today's discussion, we are going to discuss about the biodiesel. Okay. So yeah, so if you look around the Indian crude oil import, so it is 202.85 MMT in 2015-16, and the annual growth rate is around 7%. Okay, and if we take the two major fuel consumption, that is the petrol and diesel, in case of Indian consent, so you can find that the demand for diesel and petrol is going to rise up to 110 million metric ton and 31.1 million metric ton by the end of year 21 and 22, and 2017 it was just 80.4 and 26.1 respectively. And at the same time, if we just look around the biodiesel production, that is the biofuel production. So this biofuel is nothing but it includes all these scenarios. Okay, so it may be the bioethanol, bioethanol, everything. Okay, so uh, the production is increased from 27.9 million tons of oil equivalent in 2006 to 82.3 million tons in 2016, with annual growth rate of 14%. Okay, so this clearly indicates that we are just moving in the right direction, and of course the growth rate is uh, higher than the consumption of the conventional fuel, but again still it is much lesser than what we are expecting. Okay, so in Indian context, if we are talking for the biofuels, so India has rose its biofuel production from 0.15 MTOE to 0.51 million tons of oil equivalent. Okay, and there are change in the government policies, so which are now in much favor of the oil biofuel production, like minimum pricing has been monitored quarterly, and they have changed it. Okay, so this is somewhat beneficial for the production. Okay. Now, what is biodiesel? So you might have discussed this in previous talks also. Okay, so I will just briefly take into consideration. Okay, so biodiesel is nothing but the alkyl esters of the fatty acids, and typically which type of feedstock we can use for biodiesel production. So we may use edible oil, that is sunflower, soybean. Okay, so whatever it may be edible grade, we can use it. Non-edible grade, so that let's take example of the rubber seed oil, then Jatropha circles. Okay, so these are the non-edible oils. Then waste cooking oil. Okay, so which what say increasing the food chains, like your the frying food that is selling. Okay, so it may be the Burger King or any type of. Okay, so they consume lot of cooking oil, and after 3 to 4 times of frying the patty and all other eatable items, uh, the oil property declines. Okay, and with this declining property, we cannot consume it for the good health. So they have to discard it, and the amount is now increasing in the quantity wise also, and we can convert it into the value-added products by using it as a feedstock for the biodiesel. Then animal fat. Okay, so this is not having a big portion in countries of India, but yes, in case of China and some other countries, they are producing it in a what say big quantity, and they are planning to utilize this animal fat. Okay, and they can convert it into the biodiesel. Okay. So animal fat, then the algal biomass. Okay, these are the what say low cost and low grade feedstock, and we need a special treatment for such type of feedstock. Whereas edible are the, you can say, that is a most easy feedstock which can be converted into biodiesel. Non-edible oil and the waste cooking oil require some attention, but yes, they can definitely also convert it into biodiesel easily. And catalysts, so alkali, acid, and lipase. So these are the three common catalysts people are using. There are some processes which are developed without using the catalyst also. So they use the supercritical conditions of the methanol, and at that condition they don't require any catalyst. So if you look around the reaction point of view, so overall reaction scheme looks like triglyceride plus 3 moles of methanol is required because of catalyst. It is a reversible reaction, and at the end of the reaction, we are getting the 3 molecules or 3 moles of the biodiesel. That is the if you are taking methanol, then it is a methyl ester of fatty acid. If it is ethanol, then it is ethyl ester. And conventionally, we prefer to take the methanol, because when we increase the alcohol chain, so the conversion rate and the yield is going to be decreased. So that's why methanol is more preferred as compared to higher alcohol. So if we are considering the elementary reactions, so there are 3 elementary reactions. So first, triglyceride is converted into diglyceride, then di to mono, and mono to glycerol. Okay. So this is very basics about the biodiesel. And when we talking about biodiesel, so feedstock is one of the most important parameters, because if you are producing a biodiesel and the cost economic analysis, so you will find that 50 to 70, or sometimes it is up to 90% cost whatever production cost is required, that can be consumed in just taking the raw material, that is the feedstock. And typically 80 to 85% of the overall feedstock cost goes to the oil collection and oil pre-treatment. Okay. So overall, this type of feedstock, whatever is reported, they can be classified into the three generations. So first generation, it is edible oil such as soybean, rapeseed, sunflower, coconut, groundnut, palm, etc. So they contain very low free fatty acids, and because of that, you can use homogeneous acid or homogeneous alkali catalyst. And if you are using alkali catalyst, you will get the biodiesel in just less than 30 to 40 minutes of reaction, and that is up to the 90-95% conversion. So that is the advantage of using first generation feedstock. Then second generation feedstock. So if you are considering the non-edible oils, so neem, karanja, jetopa, rubber, cassava, moa, etc. These are some additions. Okay. Then animal fat, waste tallow, lard, waste cooking oil. This can be considered under the second generation also. So this contains sufficient amount of free fatty acid, and because of free fatty acid, we cannot use the homogeneous alkali catalyst, that is NaOH and fuel directly. So we have to either go with acid catalyst, or if you want to go with the alkali catalyst, so we have to go for the two-step processes, that is the esterification and then the transesterification. So in esterification, our target is to convert FFA into the free fatty acid, and once the level bring down to 2% of the overall oil compound, so we can go for the alkali-based catalyst. Okay, so this is about it. Then the third generation is the microbial biomass or the lipid, and this required a special treatment because not only FFA, but here the water content is also too high. And when the water content is there, so reversible nature is also occurring. So that's why the microbial biomass or the lipids, if we are using as a feedstock, so we typically try to use the co-solvent method where we can minimize the effect of the impurities like water. Okay. Then in my talk, I'm going to discuss about the process intensification approach using the ultrasound. So what is ultrasound? So ultrasound is basically the sound waves which is below hearing range frequency, that is 20 kilohertz to 500 megahertz. Okay, and when the sound waves pass through the liquid medium, so it progresses through the compression and the rarefaction cycle. So if we take the pressure amplitude, we can find that just due to the pressure variation, some cavities are created. And these cavities in due course of time in coming compression and rarefaction cycle, so they get enlarged, again get compressed, again get enlarged, and again get compressed. So during this compression and enlargement, so whenever they get enlarged, so the surrounding liquids can enter into the cavities, okay, and they get vaporized. And once in the compression cycle they move, so they can again get compressed. So a point will come where the pressure inside the cavity reaches to a maximum level, and there further no compression can be possible. So they get transiently collapse, and when they get transiently collapse, so they produces very high temperature pressure conditions. So temperature goes up to 5,000 Kelvin and pressure up to 1,000 atmospheric pressure. Okay, but the condition that they are generating, it is so spatial level, so narrow level. So if you are collecting a radius, so you will find that up to 5 nanometer, 10 nanometer, the effect is there. And overall, if you are considering the reaction system, so you will not find significant change in the temperature. But yes, for a continuous period, you can find that there is a rise in the temperature, okay, of the liquid medium. It may be 2 to 5 degrees for, let's say, 10 to 15 minutes. Okay, so that again depends on the various factors: what frequency, what power amplitude, and which type of ultrasonic instrument we are using. It may be bath, it may be probe, because everyone has their different power dissipation in the system. Okay, and when this system is creating the transient collapse, so they generate physical and chemical effects into the system. So physical effects generally are nothing but the mixing of two immiscible phases, resulting in a microemulsion, then micro turbulence, jet waves. Okay, so these are the physical mechanism, and in chemical effects, you can find that the free radicals are generated, when typically water or any other solvent vapors are get collapsed, so you will find that H radical, OH radical can be easily generated. Okay, if you are taking water also, if you are taking methanol also, you will find such type of radicals, and these radicals can be able to initiate a lot of chemical reactions, and this is why ultrasound is treated as one of the best process intensive technique, because here we can get the dual benefit. One is physical improvement, that is the we can reduce the mass transfer barrier by improving the mixing and dispersing of all the reactions into each other, and to get a very fine emulsion. And at the same time, in the case of the chemical thing, we can get the free radicals, which are highly energetic and they can carry out several reactions. Okay, so so this is about the basic, and let's talk about the two case studies. So first one is the acid catalyzed process. Here I'm using the blend of four different oils. Okay, and I have prepared this type of catalyst in during my PhD. So this study is from there. It is already published in the industrial and energy INDC. So ACS INDC. You can find it there also. Okay, in 2018. So what chemicals I have used? So I have used sulfuric acid, then chlorosulfuric acid, methanol. Okay, and I have prepared the anhydrous methanol by the distillation process. And for the feedstock, I have used the crude jet oil, castor oil, waste cooking oil, and the palm oil. Okay, so this palm oil again it is in crude form. It is not what to say, edible grade, and I have used it. So then for the catalyst, so in this case, I have taken the de-oil seed cake from the rubber seed. So the rubber seed oil I have used in another study. So after the extraction of the oil, whatever the de-oil cake is was there, so I have used that de-oil cake and I have converted it into the acid heterogeneous catalyst. Okay, so I have blended this crude jet oil, crude castor oil, waste cooking oil, and palm oil in different ratio. So the jet oil is 20%, castor oil is 10%, waste cooking oil is 40%, and palm oil is again remaining is the palm oil. Okay, and when I blended it, so I have checked the initial properties. So based on that initial properties, I have to make some decisions which type of process I'm going to use and how it is going to be get impacted on the final production end. So the acid value, that is 12.42 mg KOH per gram, density is 0.921 gram per ml, viscosity is 28.95 millipascal second at 40 degrees centigrade, and the average molecular weight, which can be calculated using the difference between the saponification value and acid value divided by the molecular weight of KOH. So it is coming 883.4 gram per mole. Okay. Now you can see clearly here. So this acid value is quite high. It is sufficiently greater than 2 mg/kh per gram. So that is the standard limit for use of direct homogeneous alkali catalyst. So naturally, I cannot go with the alkali catalyst. And if I go with alkali catalyst, so I will get at the end the soap formation, which is not desired at this stage. And that's why I have selected here acid catalyst. Okay. So the catalyst preparation. So the briefly I have written here. So de-oil cake was taken out and it was dried at 110 degrees centigrade for 3 hours. So if any your solvent is there, hexane, so that can be evaporated and you will get a fine or bone dry de-oil cake. And then we know that sulfuric acid is one of the strongest acids, but there are a few more acids which are more stronger than the sulfuric acid, and they are known as the super acid. Okay, so I have selected sulfuric acid and chlorosulfuric acid for the preparation of catalyst. And for making the catalyst, I have taken the ratio of 1:2. So 1 gram of de-oil cake is mixed with 2 ml of acid. In first case with sulfuric acid, in other case with chlorosulfuric acid, and roughly it is mixed for 30 degree at room temperature, and then it is calcined at 300 degrees centigrade for 5 hours in a muffle furnace with a temperature ramp of 10 degrees centigrade per minute. So at the end of calcination, the catalyst was taken out, okay, and it is stored in the desiccator. Later, the physical properties like XRD, XPS, SSA immediate, then surface area, total acid density, everything has been evaluated. And based on the highest quantity, I have selected the catalyst for the further experiment. Okay. And here to have the analysis, how the catalyst is performing, how the esterification, transcription is going to be occur if you perform it simultaneously or in the different stages. So that's why I have selected three different categories of the experiment. The first one is transcription process. Here optimization was done using the statistical design, and the single step process. So that means here esterification and transcription is conducted in a simultaneous manner, and the parameter are optimized accordingly. And once the parameter are optimized, then the same process was carried out at using the at the same optimized condition using the two different steps. That is, esterification is separately carried out, and then transcription is carried out. So esterification typically carried out with the homogeneous acid. So that was the standard, and it was optimized previously in earlier studies. So I have used that one. And then for kinetic and erroneous analysis, so I have carried out some more experiments, and typically what we do, we use the homogeneous kinetic model, that is zero order, first order, second order, third order. Okay, and here I'm using the heterogeneous catalyst. So I have selected typically the Euler radical model. Okay, so what is Euler radical model? I'm going to explain in the next slide. Okay, so I will discuss that in detail. Okay. So yeah, so this is the Euler radical model. So Euler radical model is nothing but what? It assumes that one of the reactants comes to the active site of the catalyst, then they form the activated complex, and that activated complex reacts with the another compound from the bulk. And in this way, the product is forming on the catalyst surface, and later that will get your dissolved into the bulk, and then the catalyst site is free, and the whole chain reacts continuously in the cyclic manner. So typically when we say this is a elementary reaction, so it is very easy because the reaction is going to be occurring in one state. But in case of biodiesel, the reaction is occurring in the three steps. Okay. And again, here we have two phases. One is methanol, so that can be considered as the aqueous phase, as well as the triglyceride, which is, it can be considered as the organic phase. Okay, and we have to select the proper phase which is going to get added on the catalyst surface. Okay, and we found that the solvent, that is methanol is going to get added on the catalyst surface because the surface area and the surface structure gives clear indication that the nature is little hydrophilic in nature. Okay, so that's why the solvents are going to get absorbed, and organic quantity they are not going to get very easily absorbed on the catalyst surface. Another thing to select the methanol as the absorption species, because when we add triglycerides, methanol, and the catalyst into the conical in the beaker round bottom flask, we find that organic layer is on the top, methanol is on the lower layer, and the catalyst is going into the methanol layer. So that means the surrounding element or the surrounding compounds are the from the solvent. So that's why I have selected here methanol as the absorbing element. Okay, so chemically, if I want to write it, so I can write into different stages. Okay, and the most important thing of any complex kinetic model is that every individual step becomes the elementary. So they are the first order reaction. Okay, so here the active site, then the methanol is going to give you activated complex on the catalyst surface, and this is the rate expression for it. Then the next reaction part, so reaction is going to be occur in the three different stages, and these are the rate constants or the rate expressions. And then the last one, so here biodiesel is forming, and biodiesel is getting dissolved, and that's why the catalyst spike is getting again reutilized for the methanol absorption. Okay. So this is the overall rate expression. Okay, now there are a lot of mathematical steps are available for these steps. Okay, and based on that conditions, okay, so using some assumptions, pseudo steady state conditions, so where the intermediates are not highly stable, as soon as they form, they will either get backward into the previous content or they get consumed in the next reaction. Okay, and whatever the small quantities of these intermediates are available, they are not going to affect the bulk concentration of the reactants as well as the product. So based on these assumptions, I have solved this mathematical formula, and these are the final restrictions that I am going to use it. Okay, so now you just look around the complexity of this type of mechanism. Okay, so simply if we are considering the single first order, second order, we will get the simple rate expression and we can easily solve it based on the time profile. But in case, okay, in this case, we can find that each of these rate expression, it may be the consumption of methanol, consumption of triglyceride, diglyceride, monoglyceride, or the formation of biodiesel or the glycerol, you will find that from K1 to K5, everything is available. Okay, and if you check it, okay, so you will find that triglyceride you can measure. But how to measure the concentration of diglyceride and monoglyceride? Okay, because it requires the continuous thing. Okay, and most importantly, even if you take a single oil, so that also consists of different type of elements. Okay, so it may be the triolene, or it may be the C17, C18, it may be C14. Okay, palmitic. Okay, so there are different types of the triglycerides available, and measuring their individual diglyceride monoglyceride quantity is quite tough job. Okay, so that's why this type of models are really complex in nature and they cannot be solved very easily. And I have used MATLAB for this. And typically in MATLAB, we use the OD solver, and that is coupled with the genetic algorithm. Okay, so genetic algorithm and OD solver, I'm going to discuss in the next slide. Okay, so before going to the kinetic analysis, so let's discuss about the characterization and the physical properties of the catalyst. So first characterization is the XRD. So here you can see from the picture. So this is the raw carbon. So this is the D oil take only. This is the sulfuric acid treated carbon. Okay, so this is the, and this is the chlorosulfuric acid treated carbon. Okay, so you will find that the peaks are just strengths are increasing. Okay, typically for the 002 and 101. Okay, so this 002, it gives the characteristic nature of the amorphous carbon and unsymmetrically oriented polycyclic aromatic carbon chains. Okay, so that means there may be chance that the rough surfaces are available, and we can we can easily capture this for the absorption of the methanol. Okay, and this low density peak, that is, sorry, this is 101. Okay, so this gives the graphitic structure. Okay, so graphitic structure means here we can find that some what is the activated compounds like sulfuric group can be available, and that can be act as an active site. Okay, and you can find that it is more in case of the chlorosulfonate. Okay, then whether it is sulfur is really bonded or not, or whether the acidic sites are really available or not, to confirm this, we have done the XPS analysis. Okay, so X-ray photospectrometer. So this XPS spectrum for both the catalysts, when we see, so we can find that oxygen is available. Okay, then carbon is available. So carbon is the basis, so that's why it is giving you strong peak. Then sulfur is also detected in the analysis. Okay, and this red will indicate the your sulfuric acid treated, and the black is going to deplete the chlorosulfuric. And you can find that the intensity is always higher in the chlorosulfuric acid treated. So that means if we are considering the sulfur, if we are considering the oxygen, so we find that more sulfur and more oxygen is getting incorporated in the catalyst. Okay, if you do the narrow scan, we find that the carbon, this is the bulk carbon. So this peak is due to the bulk carbon available in the D oil cake, and this gives a slightly acidic structure. So that means there may be some cellulose or any other type of material in the D oil cake, and that is get converted into some carboxylic acid because of the sulfuric acid. So this is representing the COH. So this is again gives you negative. So that means this in acidic behavior. Okay. Then when we do it for the sulfur, we found that the sulfur is available in the 2p region. Okay, so 2p region is giving idea that the minus the or SO3H group is available. Okay, so this SO3H group is the major active site for the further reaction. Okay, then efficient. So to check whether the porous catalyst porous or not, and how the porosity is there, we have done the efficient, and we found that this is a sulfuric acid treated, so it is also porous. Okay, but you can see the porous structure is not as that of this picture. Okay, and this is the chlorosulfonated. Okay, and you can find that the pore size is also bigger, number of pores are also much higher, and this is what exactly we need for a good catalyst. Okay, and why we have selected chlorosulfonic acid? Because chlorosulfonic acid has two functions. One is chlorine, another is sulfuric acid. Okay, so sulfuric acid is going to get attached, and that was reported previously in some literature, so no issue. But the problem is with the surface area and the pore size. Okay, to improve the pore size, we have used the bifunctional acid. So this bifunctional acid, when they react, so sulfuric acid react with their intensity, chlorine react with their intensity, and during the calcination, the chlorine get out as a Cl2 gas, and when they get out, they will create more porous structure as compared to this one. That's why we get the highly porous structure in case of the chlorosulfonic acid. Okay, then we measure the surface area, and the same thing can be found out very differently. Okay, so surface area, if we compare, so surface area, we can find that for the chlorosulfonated it is 10.208, and it is for 16.187. Okay, yeah, you may ask me question that this is not that was standard. Okay, but yes, from machine to machine it was vary, and whatever the machine instruments we have used in IIT, that was too old and it was not functioning that to the proper mark. So that's why we have kept the condition instrument same, so that we can mark the enhancement while we comparing the both the things. Okay, and the pore size also, you can find that the pore size is also much higher in case of the chlorosulfonic acid, and that's why we have selected chlorosulfonic acid for the further analysis. Okay, and the total acidity, the protocol is provided in the literature. Okay, so here we have to take the catalyst sample, we have to dissolve into it, we have to heat it up to certain mark, so that whatever the acidic groups are there, they can be easily accessible, and then we have to titrate against the alkali. Okay, known quantity of alkali, and then we can get the acidic site. Okay, and with this acidic site, we can find that the more acidic sites are available in case of the chlorosulfonated catalyst as compared to the sulfonated catalyst. Okay, so these are the overall justification or the analysis that we got from the characterization of the catalyst. Okay, then optimization. So optimization, we have used here statistical optimization. So statistical optimization, at the end you will get some experimental design, and when you perform the experimental design, and you get some analysis, and once you put that again to the software like Minitab or the design expert, you will get one quadratic equation. Okay, and this quadratic equation, if you put the parameters and you solve it, you will get the maximum expected output from the process. Okay, and the quadratic model predicts here the maximum transmission can be achieved at yield will give it 90.56% at a molar ratio of 12.8:1. So that is 12.8 moles of methanol corresponding to 1 mole of triglycerides with a catalyst filling of 8.18%. Okay, so here 8.18% is catalyst higher, but you should understand this study or this optimization was carried out for simultaneous esterification and transesterification. Okay, so simultaneous esterification transmission, it is slow process, and when you are considering the acid catalyst, so they have the slower kind. So that's why it is coming here. So little higher concentration of the catalyst as compared to the homogeneous alkali catalyst. Okay, and reaction temperature is around 62 degrees centigrade. Okay, all the experiments were carried out for 3 hours, and when the validation experiment is performed, you will get 91.2 experimental yield as compared to the predicted was 90.5. So this is the average of 3 experiments. So there may be some plus minus error, and till it is in the range. So that means whatever models we are selecting, whatever process parameters we are selecting, so that is in the good order. Okay. Now, once we did the optimization, then what we did, we use the same optimization parameters, and then we carried out the experiment in the two steps, that is the esterification and transcription. So for esterification, we have selected 3 weight% of the sulfuric acid, 6 molar ratio of the alcohol, and the reaction was carried for 1 hour. And then whatever the product is there, we have separated, the methanol is taken out, and then we have analyzed it. So we found that again acidic value is decreased, but not up to that mark. So that's why we again selected to go with the heterogeneous acid catalyst. Okay, and when we do the heterogeneous catalyst, so we know that we are not going to get for these conditions for 3 hours. So we taken out sample at every interval of 15 minutes, and we found that at the end of 1 hour of reaction, we are getting the same or the higher conversion as compared to the 3 hour of previous reaction, that is the esterification and transcription simultaneously. So here, instead of 3 years simultaneous, we have carried out esterification for 1 hour, then separation, and then we have carried out the transcription for 1 hour, and we are getting the higher expected results as compared to the single reaction. So this is one where we can think that yes, the equilibrium can be seen when the water is available, and when we separate out the water, that is a byproduct of esterification reaction, we can achieve the higher product yield, that is the desired one, that is the biodiesel. Okay, and the reaction expressions I have showed you in the previous slide. Okay, so if you just take it K1 to K5, the target is to get the K1 to K5. Okay, and with MATLAB, the ODE solver coupled with your genetic algorithm, we are getting the different rate constants, and this is for single step process. This is for the 2-step process. Okay, 2-step process when I mean, so it is only for the second step, that is the transcription. Okay, and this control experiment is used means it is with mechanical agitation. So here I have used the magnetic stirrer at RPM of 600. Okay, and this is a test experiment. This is the with ultrasound, and here I have used the ultrasound bar, and the frequency is 35 kilohertz, power output is 35 kilowatts. Okay, and this what is it, the reaction mixture, the round bottom flask pipe, condenser, flow water, everything, other process conditions remain the same. Okay, so you will find that the K1, that is the absorption coefficient, it is little higher in case of the mechanically agitated system if you compare with the ultrasound assisted system. Okay, so in any case, you can find it. So you will find it is little higher as compared to the ultrasound assisted system, whereas all other kinetic parameters, that is K2, K3, K4, K5, they are lower in case of mechanical agitated system as compared to the ultrasound assisted system. Okay, and if you take the cumulative error, because we are using the function where the error should be minimized with the experimental result and the kinetic model result, and we find that the error is under a certain limit, so there will be no chances of getting any other error. Okay, so the basic analysis suggests that when we are testing the reaction with the ultrasound, so what happens, as I previously mentioned you, during the transient collapse of the bubbles, you will get the physical impact also. So that is a micro jets are getting out. Okay, micro turbulence are created. So that actually what say gives you generation of small shock waves, and that small shock waves will revert the absorption of methanol on the active side, and that's why we are getting a slightly lower value in case of the ultrasound system as compared to mechanical system. But when the reaction parameters are considered, so where the mixing of these two reactions is required, and at the same time the absorption of methanol is required, then that absorption should form the complex, and that should come into contact with the triglyceride, that should be happen in the efficient way. You will find that the ultrasound system will give better results. Okay, and in overall comparison also, if you compare the graph that is on the next slide, you will find that the overall conversion in the mechanical system is much lower as compared to ultrasound system. Okay, so here you can find that the first graph is a single step process with ultrasound, and this is a single step process with the mechanical. So you can check the biodiesel yield. So it is 0.02 mole, okay, at the end of 3-hour reaction, okay, or up to 0.023. But here at the end of 3-hour reaction, we are getting up to 0.027. Okay, so yield is also higher at a faster rate, though the rate constant of the adsorption step is lower. Okay, but that can be consolidated or compensated on the kinetic parameter, that is K2, K3, K4. Okay, and when we use for the same analogy for your two-step process, you can find that the same thing can be again getting improved up to 0.03 mole, okay, on the molar basis. And again, reaction time is 1 hour, and as compared to the higher yield as compared to the mechanical system. Okay. Then we have done the kinetic analysis. So we extended this kinetic analysis to the your RNS analysis. So RNS analysis is what? It gives you basic idea how much energy is required to form a complex that can be further take part into reactions and give the final. Okay. So if the activation energy is less, so that means reaction can easily process very easily. Okay. If activation energy is more higher, so that means it is a mass transfer limitation and you have to provide more energy, or whatever energy you are providing, most of that energy is getting consumed to overcome that the mass transfer barrier as part of the activation. Okay. And we have conducted experiment at some different temperatures with the optimized conditions, and whatever analysis we got, so means we have K1, K2, K3, K4, K5 at optimum conditions and plus 2 other conditions, and for each case, that is the 3 reactions, the K2, K3, K4, we plot the activation energy, and this is the activation energy, and this is the overall activation energy of the process. In all the graphs, you can find this. Okay, and you can find that for the single step process with ultrasound, the activation energy, okay, how much it is. So these are the rate constants for your identification. I have put in the tabulated form, and corresponding activation energy. You will find that for the first step, it is 19.43, 15.75 for the second step, and third step is 15.69. And overall for the ultrasound is 9.62. Whereas if you compare the same process, you will find that it is higher in case of all the individual steps also and on the overall reaction step also. That means whatever results we are getting, okay, so that are confining the model that we have selected, it is suited for that process. Okay, if we are getting this reverse data here, and final output, experimental output different, that means whatever assumptions we have selected, or whatever the thing that we have started to derive the equation, that is the methanol is absorbing on the catalyst, that is not true. But here we are getting the same type of results. So that means whatever the starting assumptions or the starting consideration we have made, that is holding true here. Okay. If you consider the two-step process, so that activation energy is again getting reduced if you compare the ultrasound resistance process as well as if you compare the mechanically process. Okay, so that means the water available as a byproduct from the esterification reaction is going to make a big hurdle for the trans-esterification reaction and making the reversible nature more significant in case of the single step process. Okay, and in two-step process we are eliminating that water, so that's why we are getting higher conversion at lower amount of energy and even in lower duration of the time. Okay, that means kinetic constants are increasing, rate is getting speed up, and we are getting the higher product in a smaller time. Okay, so if we just compare these three, so you can find that 51.87 out of 69.6, so it is the kinetic, so it is the kinetic, and remaining is the mass transfer barrier. Okay, so in case of, you can find it is 53 and it is 75. So you can find that the mass transfer barrier is little lowered here also. If you again compare this two, so here we can find that the stringent effect of the ultrasound, okay, where the mass transfer barrier is getting reduced quantitatively as well as the kinetic amount of the kinetics also getting improved significantly when with sudden decrease in the overall activation energy of individual steps as compared to mechanical agitating system. Then whenever we are preparing any catalyst, so it's always advised to take its reusability. Okay, and higher the reusability, higher is the what is it, important that catalyst we can commercialize it very easily. Okay, so I have checked it for up to 3 cycles. Okay, and later I have not checked it, but up to 3 cycles, whatever I have resulted. So I have selected the optimum condition, the chlorosulfonated acid catalyst, and after each cycle, the catalyst is separate out. Okay, it is just washed little with methanol. It is dried and it is recycled into the next batch. Okay, and same was done for the single step as well as the two-step process. And you can find that single step process, the activity or the this is the triglyceride conversion, it is going to be drastically reduced. This means that whatever water is produced, that also leaching out the acidic side. Okay, that's also leaching out the acidic side, means whatever the acidic groups are available, SO3H or ethylene, so they are also getting saturated and they are coming with the water side. Okay, so that's why we are getting the significant reduction in the final yield as compared to the two-step process. So because in two-step process we don't have any water content, and with this case we can easily say that yes, we can achieve the consistency in reusability when we are making that two-step process, that is the separate esterification and separate transesterification, and we can get the higher conversion in terms of the commercialization. Okay, so whenever we are thinking for the commercialization, so people conventionally try to use the homogeneous catalyst, and homogeneous catalyst when we use, so there are some drawbacks. We need to use more and more water for the downstream processing, and whatever the spent generated or the equivalent generated, that we have to treat out. If it is a heterogeneous catalyst, so we can easily reduce the quantity of the effluent. We can recycle the catalyst easily, and that will less hazard the environment in overall time. Okay, so these are some outputs for the study, and that gives you idea. Okay, so if I have to oversynthesize of this study in terms of the reaction yield, in terms of the activation energy, so these are the 4 points. So the process is optimized where I'm getting 91.2% plus minus 1.1% and 93.7 plus minus 1.3% at the optimum condition, that is 12.8, it's 1, catalyst coding 8.18, temperature 63 in single step and two-step process. In two-step process, the activation energy is much lower. Okay, it is 55.98 as compared to the two-step process, single step process. Then the individual activation energy gives you analysis that predominant role of ultrasonic process intensification was observed in two-step process, where sum of activation energy, that is the activation energy of three reaction states, okay, which are very lower as compared to the mechanical agent, that is 14.07. Okay, and the catalyst can be recycled up to 3 cycles effectively in this study, and only 10% loss is occurred in two-step process, where significant loss in the active catalyst in the activity of the catalyst, that is 40% in the single step process is observed. So this is the first part of the talk. Okay, so so the next part of the talk is related to the interesterification process using heterogeneous catalyst. Now, what is the difference between the transesterification and interesterification? So in interesterification, we are replacing methanol with methyl acetate, and at the end of your product, you are getting biodiesel. Okay, so that is again fatty acid methyl ester, and instead of glycerol, okay, so you will getting triacetylene. Okay, now what is the advantage and disadvantage? We are going to discuss both. So advantage is that the both phases, methyl acetate and the triacetylene, they are completely miscible, so there is no mass transfer barrier for this. Okay, so the kinetics is higher, the conversion is higher. Okay, and whatever byproduct you are getting, that is here is triacetylene, it has more commercial value as compared to the glycerol, because whatever glycerol we are getting, glycerol is a high demand in the pharmaceutical food industry, okay, in the cosmetics, okay, but the biodiesel, the producing the glycerol, it consists of contaminants. It consists of the alkali, acids, or methanol, and that's why it is getting lower commercial value. But triacetylene is having higher value if we getting purified in terms of it. And if you don't want to purify, then also no problem. We cannot. If you don't want to separate out, then also no problem, because triacetylene can also be used as a fuel additive in case of the biodiesel diesel mixture. Okay, it can be used as a viscosity improvement additive. Okay, these are the advantages. But what are the disadvantages? So disadvantages are, if you use methyl acetate instead of methanol, the cost of the process increases significantly. Because if you compare the cost of methanol and methyl acetate, so methanol cost is around, let's say, 35 to 40 liters commercially. So methyl acetate is almost 2.5 to 3 times higher than that of the methanol. Again, purity. So methanol you can get 98% pure, but methyl acetate purity is little less. Maximum you can get 98%, and yes, in analytical grade and all of them you will get little lower also. Okay. So here we are using the again the blend of the different non-edible oil feedstock. Okay, and again the same thing is going to be occur. So whatever we are starting with this, so we measure the physical properties, and we found that the acidic value is much higher. Okay, so we cannot use the alkali catalyst directly. So this CO2 cuprous oxide is alkali catalyst, and to use it we need two-step process. So esterification is carried out using the sulfuric acid and methanol. Okay, and for the the second step process, we are using the cuprous oxide as catalyst and methyl acetate as the solvent. Okay, and yeah, so this is the overall scenario, and there are very limited studies are reported with the use of heterogeneous catalyst in case of interesterification process, and majority of people try to use it the enzyme catalyst or the critical conditions, so there will be no need of the catalyst. Okay, and that's why I have selected the heterogeneous catalyst, and in that case, as the condition changes, here the both reactants are completely miscible and they can compete to get absorbed on the catalyst surface, so we cannot use the illeradical mechanism. Okay, so here we have to use the much more complex mechanism, that is the LHHW, Langford Fisherwood Hagen Watson kinetic model. Okay, so what is the reaction steps and what are the things we are going to discuss in the upcoming stages. Okay. So this is the composition and these are the physical analysis. So based on these two things, we have to decide it, and once we decided it, so this is the plan of action. So primarily specification was carried out using the sulfuric acid and the methanol, and after that the sulfide oil again it can be separated from the methanol and the acid completely. If methanol is there, then naturally the kinetics is much higher for the methanol, so we don't want to get any impact on the intensification reaction. So that's why rota vapor was used to recover complete methanol from it. Okay, and the specified oil is stored, and then further it can be used for the intensification processes. Okay. So again, process optimization was carried out using the CCD, that is the central composite design, statistical design. Okay, and here we have used the 3-parameter, 3-level optimization, which gives typically 20 experiments. Okay, you can use Design Expert or Minitab in software. Okay, Design Expert is freely available. Minitab certificate trial is available. You can use it. Then the absorption of reaction species on catalyst surface is required, because here absorption is going to be play a major role, and which species is going to be get absorbed more predominantly, that we have to analyze. Okay, and accordingly we have to correlate the other species. Then here we have done the kinetic and the thermodynamic analysis. So thermodynamics again the RNAs analysis and similar way. Okay. The analytical method. So previously also I have used the NMR spectroscopy to get the conversion of the triglyceride into biodiesel. Okay. But here additionally I have to study the absorption coefficient. So for this case I have used the HPLC, and these are the specification of the column, then the detector and the model of the HPLC. Now, what is this LSHW kinetic model? So previously, I have told you that only one reaction is getting absorbed, and that is reacting with the bulk from the bulk reactant of from other reactant is the bulk. Okay. So in this case, it is not happening. Right? It is that both reactions should absorb on the catalyst surface. They should form a complex, and that complex should get reacted, and they will get the product. So this is the difference between the LHSW and the irradiated. Okay. Now in previous case, it was very easy that we can say that the two different phases are available. Catalyst is going in that phase, so that's why we can go with the irradiation. But in case of LHSW, we cannot say that only dominantly methyl acid will absorb or dominantly triglyceride will absorb. Okay, so keeping the nature of the catalyst, methyl acetate has a higher affinity, but again, methyl acetate is not that much having higher affinity as compared to methanol. Okay, so affinity decreases, and at the same time, the solubility when increases, so catalyst is getting readily available for both the phases, and because of that, we cannot predict that this is going to be predominantly active sites are occurred by the methyl acetate and not by the triglyceride. Okay? So because of that, we have used here the LHSW mechanism. Okay. Now, the major problem with this study is that previously case I can say you that these are the reaction species. Only this thing is getting absorbed. Methanol is getting absorbed. I have the sequence of the steps. Okay. Here also I can use the sequence of steps. Okay, so I can use this methyl acetate is getting absorbed, then triglyceride is getting absorbed. So this is the absorption part. But when the reaction part comes, I cannot write the three reactions. Okay, if I write it, then the what you say, your absorption coefficient and the rate constant, they will increase tremendously. And getting the exact quantity or quantification of these intermediates is very, very difficult. Okay. Anyhow, if we can get the quantification, then their absorption on the catalyst surface is again a difficult part. So that's why here we have used the single reaction. Okay. And if you check with the previous study, if you check with the data, you will find that in transcription reaction or whatever the conversion of triglyceride, you will find the first rate, that is K2. Okay, so K2 is always higher in all the cases. Once this triglycerides from the diglyceride monoglyceride, they are more easily get converted into the biodiesel. But this is the if you are considering this three elementary step, so this is the most resisting step. So that's why here we have considered the single step mechanism and assuming that the conversion of triglyceride to diglyceride is the most resisting step. Okay, so these are the rate equations, and here if you are considering the absorption, so we have to consider the equilibrium constant. Okay, and these are the forward and backward reaction rate, again absorption coefficients. Okay, these are the notifications. Now here we are considering only the single step, so that's why we can write the forward versus backward reaction and divided by the overall your absorption coefficient. And again, for the single step, we are getting this much complicated equation. If we write the three major steps, the equation getting too much complicated, and that unknown parameters cannot get solved. Okay, so here also we have single rate. So one rate equation, if you have one constant, then can be solved. If you have two rate constants or the two constants and single expression, then that can be identified by converting one into another. But here, how many constants, just count it. Okay, so this is first, second, third, fourth, fifth, sixth. Okay, and yeah, total how much? Yeah. So 1, 2, 3, 4, and 5, 6. Yeah, 6 constants are available. So single reaction and 6 constants, and we have only one data, that is the conversion of triglyceride to biodiesel. Okay, so this is one of the biggest challenge, how to solve this type of equation. Okay, so when we look around the literature, we found one good reference in one of the oldest books in the Kipling 1965, where they have studied the material balance. So they have studied the material balance of the isothermal non-reactive binding system, and from their observation, they have given this type of expression. Okay, so this N0 is nothing but the initial moles of the any component in the binary system. Delta X is nothing but the change in the moles of that system. M is nothing but the mass of the catalyst. Okay, and this is how the change can be considered. Now, In another study reported by Song et al. In 1998, they have used the same equation, but they have modified in terms of the activity coefficient and in terms of the absorption coefficient, okay, equilibrium constant, okay. So with these two equations, if we solve this equation, so we can get it, okay. So in the first equation, what we know, we can know this quantity change by the initial and final change, and that's why we have considered the HPLC analysis. So we have considered known amount of the catalyst, that is the optimum catalyst we are getting at the end, and we are taking the non-reactive. So we cannot take the methyl acetate and the triglyceride. So we have to take a pair like this, one product and one reaction. Okay. So three pairs can be formed like methanol and with the methanol. It is methyl acetate with your triacetane, then methyl acetate with your biodiesel, and your triglyceride with methyl acetate. Like this, we have to form the permutation combination, and we have selected a lot of experimental permutation combinations at different molar fraction change. And once we get this thing, so by the end of HPLC results, we use this equation to generate this left-hand side quantity. And once we have this left-hand side quantity, then we use the Excel solver to optimize and to get solved and to get the final quantity of this K12 and K2. And for this getting A1, that is the activity coefficient, we have used the SPN to get the binary model constant using the NRTL. Okay, so this is NRTL model, and this is the uh, data that we have got from the SPN. Okay. So again, after the optimization, that was the first task. We are getting some conditions, and the similar condition when we conform, we will getting the good amount of biodiesel yield as compared to the predicted one. Okay, so no problem with these conditions. Okay, here you can find that the catalyst loading is also reduced, molar ratio is also lower, and temperature. So if you are using methanol, you will find that the reaction temperature is always above 60, 62, 63. But in case of methyl acetate, you will find the lower temperature. Because why? Because you can find it very easily that when the miscibility increases, the barrier in the mass transfer getting reduced. Okay. Now, at the absorption resistance, what we have done with the 0.6 gram of catalyst and different constitution of non-reactive binary systems in a 20 ml glass vial at the same reaction temperature and for 8 hours to get the final equilibrium to be attained. Okay. And once this is done, we have, these are the experimental data points for 4 different states. And this smoothness is nothing but it is the your generated data from the previous equations, equation 1 and 2. Okay. And when we find this comparison, we find that whatever the model we are selecting and data we have generated from the analysis, they are correlating with each other very effectively. Okay. Now, when we have these 3 different pairs, okay, so first pair is nothing but your methyl acetate and triacetate. Second pair is methyl acetate and methylolate, and third pair is methylolate and triazole. Okay, so we have not considered biodiesel here completely. Okay, when we are considering biodiesel completely, so again problem starts with it consists of number of components. Okay, so to minimize this component, we cannot use the actual feed. Okay, so here we have used the castor oil. Okay, so yeah, so we have used the castor oil, and typical identification is that only single component have the more than 50% initial concentration, and based on that we have used it. Okay, so here when we have these all types of data, so we will get this NS and K12. Okay, and when we have these 3 parameters. Okay, so again the problem is starts with what actually we need individual parameters. Okay, so if you take this equation, we need KMA, KP, or KF. Okay, or like this individual parameters and not the overall or the relative concentration. Okay. So individual parameters or individual concentrations getting is little difficult from this study. So what we have done, we have correlated all these 3 parameters in terms of the single one. Okay, so when we analyze this completely, we find that methyl acetate is the first preferred reactant on the catalyst surface, followed by the methylolate, that is the biodiesel, then triacetylene, and then the triolate. Okay, so based on that, what is the relativity? So if methyl acetate, we give the reference number 1. Okay, so suppose if there are, let's say, 100 active sites are available, and we are saying that methyl acetate is the one who are assuming getting absorbed on the 100 active sites. So compared to that, if biodiesel is getting absorbed, so how many active sites they will get it? So they will get 47. Then triacetylene, that is the final byproduct, they will absorb 127 active sites. And lastly, the your initial feed, that is the triglyceride. So they will get only 25 sets. Okay. Now, once we have the correlation, so we can convert all the remaining parameters in terms of only the constant of Kme. Okay. So we have done this, and we found that the expression is now little simple, not much simple. It is little simple. Now, single expression has 1, 2, and 3 unknown. Okay. So again, 1 expression, 3 unknown is little tough. So again, we have taken the help of the MATLAB, and again the same genetic algorithm system is followed. So genetic algorithm, what it gives, we have to put the equation, we have to give the initial range from which we are starting the constant of these concentrations. Okay, and with the OD solver or the RK4 solver method, the gas is initial gas is given, and based on that, the MATLAB generates 1000 population, and they will try it. Okay, so once the 1000 population is tried, so the minimum error function we have to define, and those starting conditions, they are very close to minimum function. Only 50 or 50%, that is 500, is kept. Remaining 500 is scrolled down, and then that 500 is again get multiplied and get formulated in a similar pattern, and slowly we converge our function, that is minimum error is achieved. And when the minimum error is achieved, the MATLAB gives the output. Okay, and with this output, when we run this equation, okay, we will able to generate this conversion profile at different conditions, and these are the experimental data points. And you can find that these data points are matching very perfectly or very closely with the experimental data points. Whatever assumptions or whatever methodology we are following, they are going to be get best fitted in this condition. Okay, so if it is not that much best condition, so we will get the difference error, and that error is showing here. Okay. Now, again, the same analysis, so kinetic analysis, we are trying to use to understand the mechanistic insight. So we carried out reaction at different temperatures, 55, 50, 45. This is with mechanical agent, this is sonication. Okay, and we found that the K1, the rate constants. Okay, so rate constants are much higher in case of your ultrasound system as compared to the mechanical agitated system. Okay, and overall mechanical absorption of the methyl acetate, that also gets little reduced, because whenever absorption is coming and you are considering the ultrasound, you'll find that the shock waves are generated. Okay, and microturbulence is generated. So absorption is little less, but that can be compensated in terms of the kinetics. Okay, if you look around the KOW, now KOW is nothing but the absorption divided by desorption. So you will find that this KOW is increasing. Now, just now I told you that the sonication application, when you apply the sonication, you will find that the reduction in absorption. Then how the overall KOW is increasing? Because KOW is nothing but the absorption divided by the desorption constant. So at the same time, when your absorption coefficient is decreasing, your desorption coefficient is also decreasing in the similar manner. And when you take the ratio, you will find that there is a net improvement in the overall absorption coefficient. Okay, so it's simply like that. You may have some rupees, let's say 20 rupees, and you are going to divide it by, let's say 7 rupees. Okay, so 25 by 7, so it comes around something 3 point whatever the fraction. Okay, now you significantly reduce it from the numerator as well as the denominator. Let's say you are going to reduce is 2 rupees. So from 25 it is 23, and from 7 it is 5. Okay, now you just divide 23 by 5, you will get your fraction more than 4. Okay, so decrease is there, but that decrease, if you are considering the desorption also, you will get the overall improvement in your mass transfer, that is the absorption of the reactant on the catalyst surface, and then desorption of the final product from the surface, so that active sites are more readily and more speedily available for the next cycle. Okay, and this is how the ultrasound is optimizing, or it is intensifying the process. Okay, so these aspects are cannot be studied verbally, like say that, yeah, with application of ultrasound we are getting the yield 10% higher, or we are getting the similar yield in let's say 75 instead of 90 minutes. So that are a very rough idea what exactly happening, and how this ultrasound is promoting the reactions, or how ultrasound is adversing the effect, how it is exactly performing the mechanism, that has to be analyzed. And for this case, we need to do the difficult or the complicated kinetic model analysis with using the MATLAB. Okay, so overall conclusion, if you want to study from this study, so it shows that the interdistribution process we are optimized at this conditions. Okay, and we are getting the higher yield as compared to the trans-distribution reaction. If you consider the previous study and this study, okay, so initially it was 93, here we are getting 95%. Okay, then NRTL model was used, non-random two liquid model, to study the absorption coefficient, and we find that the methyl acetate is one of the most preferable compounds on the active to get absorbed on the active sites of the catalyst, followed by methylolate, that is the biodiesel, then triacetylene and triavalene, that is the triglyceride. And the activation is energy, if we compare with the mechanical activity and the ultrasonic system, you find that 25% reduction is the computed in case of the ultrasonic system, and ultrasound improve the yield, as well as they favor the desorption of the final product, so that the active sites can be reutilized predominantly, and that is the overall process intensification we can see with application of ultrasound in this case. So this is all about my talk. If you have any queries or any questions, you can ask me.
A participant asked the question regarding the session on first discussion. Unmute your audio, just ask the question, or you have to type the chat box.
Anyone can ask questions. Yeah, Ayyappan PR. I can see that Ayyappan PR has raised the hand. So you can ask the question.
Participant ask the question. Unmute your audio and just ask the question. Just ask me.
Sir, this is Vikas.
Yeah.
Sir, why the sonification only has been chosen for this process? Are there any other methods?
Yes, there are other methods. So what is we have to understand the process intensity. So process intensification is what? We have to first understand what are the limitations of the process. Okay, so if you are considering the transition process, limitation is that the two phases, that is the methanol and the oil, they are not miscible with each other, and that is where the mass transfer barrier is coming, and we have to minimize that mass transfer barrier. So yes, definitely we can use some other approach like co-solvent method. So you can use the solvent such a way that the solubility will get increased and you can overcome the thing. Okay, so that is the one aspect. then you can use either you can think about in another way that mass transfer barrier I cannot remove it, no issue, but I can improve the kinetics. So that can be done. And for improvement of kinetics, I need to supply more amount of energy, so I can use the microwave radiation also. So that is another approach. So these two methods are available, but they significantly use target only one aspect. That is, in case of co-solvent, you are considering the mass transfer barrier, you are not considering the kinetics. In case of microwave radiation, you are considering the kinetics, but you cannot overcome the mass transfer barrier. Okay. And when you add the third compound, that is the catalyst, that is in a heterogeneous form, then your mass transfer and the kinetics both are really play an important role in the overall process intensification. So ultrasound, why I have selected here, because ultrasound, when you, as I have given a brief idea about it, you can find that the transient collapse can use you the physical as well as chemical effects inside the system. And when you consider the physical effects, you will find that the microturbulence, microgeos, shock waves, so they actually prompt one phase molecule into another phase and with a sufficient amount of energy and to a higher extent, so that they cannot come very easily, and you will get a fine emulsion of the two immiscible compounds. So mass transfer is overcome. Secondly, from the kinetic study, we have clearly seen that the activation energy is getting reduced drastically, as well as the rate constants are increasing higher way. Okay, so that means when this transient collapse occurs, the temperature pressure conditions are getting extremely high, 5,000 degrees centigrade, 1,000 atmosphere pressure. So if any molecule is coming in that phase and reaction is going to be occur, so naturally that reaction is much more higher, faster than that compared to the conventional. So heating, transfer of energy, transfer of mass is more efficient if you compare any other process. So that's why ultrasound is one of the what to say better process. Okay, I will not say the best one. Okay, because yes, there are some limitation of ultrasound. You cannot use any frequency, any power input. Okay, so the physical parameters also play an important role. But if you optimize these things and you will use it, you will get a much more efficient output as compared to other two intensive processes that can be typically used for the biodiesel production.
Thank you, sir. Thank you.
Any other question, participants? Yes, unmute.
Hello.
Yeah.
So you are using heterogeneous catalyst.
Yes.
Yeah. Say that is for the conversion of edible oil into the biodiesel form.
Yes. Actually, I have not used the edible oil. Okay, I have used a blend of the oil. So it consists of West Point oil. It consists of the crude jatropha, rubber seed. Okay, different composition I have used in different studies, and all these studies are already published. So their composition and their selection criteria is also mentioned. Okay. So basic idea about this all these studies that if India has targeted that mandatory 20% or let's say 10% biodiesel blending is required. That was we are targeting from last 10 years, but we are not achieving. But if government gives a strict rule, so we need a lot more quantity of biodiesel. And when we are talking about the diverse nature of the country, we cannot find that a single feedstock is going to fulfill all this demand. So to meet this demand, what we need whatever feedstock is available. So suppose sometimes we have, let's say, waste cooking oil is readily available, and we have very limited quantity of any non-edible oil, like say castor, it may be jatropha. Okay, so we can blend in different way and we can process the system. Okay, so if any commercial plant we are planning, we should not prefer to shut down it for lack of availability of any oil. Okay, like palm oil, it is completely imported from the Malaysian countries, Malaysia and the similar countries. Okay, so suppose somehow in Malaysia any condition happens or trade stop, so we cannot refer to shut down our plant just because palm oil is not available. Okay, so what we can do, whatever we are available, we can reduce the concentration of palm oil, we can increase the another oil, and we can go ahead with that condition. So this is the overall idea in the blended oil.
The basic component of this non-edible oil, it is a long chain compound, isn't it?
Long
There
chain compound means
Now, that means to say that if you consider biodiesel or
Mhm.
normally the diesel, where
Mhm.
the hydrocarbon constituent are, that means smaller one. They are not the longer one.
No, no, no. If
Uh,
we are considering the conventional diesel, so
hmm.
conventional diesel is typically ranging from C10 to C18, correct?
Yeah.
C10 to C18.
Hmm.
And when we are considering the biodiesel, so biodiesel again we are considering the different edible oils, and edible oils when we are considering so different triglycerides. So triglycerides again starting the carbon chain from C14 to C20, and in some cases it goes up to C20.
Hmm.
Okay, so idea of this whole process, why we are blending biodiesel into diesel? Why not biodiesel is blended into gasoline? Because gasoline carbon change is different.
Hmm.
Gasoline carbon change is C5 to C10,
Yeah.
and here we are getting starting from C14 to C20, and majority is C14 to C18. So that's why C14, C18, here also C12, C22 or C20. That's why we are using. And whatever edible, non-edible, or the animal fat you take it, you will find that the maximum carbon range will not go more than C22. So that's why we cannot what say changing any kind of it. And again, one more advantage of this biodiesel is that we have some more oxygen. So though the carbon range increases, it go beyond C20, C20 in some cases. But yes, some oxygen is available, so that will help in combustion.
So here in production of biodiesel, cost is also an important factor.
Yes, definitely.
Definitely. Okay, sir. Thank you.
Yeah.
Any other question? Accepted. Just unmute your audio and ask the question.
Any other question?
Okay, sir. It's a nice session. I think now they are asking already. It's a nice session. Lecture on the development. Thank you very much, sir.
Yeah. Thank you.
Thank you.
Thank you.
Participant, tomorrow is the last day. I will start with the first session on 9:30. Second session on 12 to 2 with 2:15 validatory. Some of the participants ready for feedback on the online tomorrow. After that, validatory it may be 10 to 15 minutes, and it will be shared to the online test link. You have to give as much as fast on test submission.
Sir,
Yes.
at what time you will have the test?
Test after a validatory is over, it will be shared to the WhatsApp also at the email group. WhatsApp group and email link will be shared. Just you click the link and
Because
submit.
time constraint is there, you know.
No, his time is given. Up to me. You have to give. As much you have to given fast answer, a submission. It will be easy to me. That will be submitted to the online. You get the certificate quickly. That is the only thing.
Okay. Thank you.